when we talked about conservation of energy and we talked about the conservation of mechanical energy? And if we had a roller coaster without friction, it would travel with a constantly changing mechanical energy, all potential energy at the top to all kinetic energy at the bottom, and back and forth. It would keep constantly changing. Well, in this case, mechanical energy is no longer conserved. You can see friction of the wheels with the track increases the internal energy of the car. So as your car moves along, your internal energy is slowly increasing. Your total energy is conserved because your increase in internal energy is equal to the decrease in mechanical energy. The heat from the car is then dissipated into the surrounding area. Still, energy is conserved. Air molecules heat up as the car cools down. This brings us to the first law of thermodynamics. Heat is a form of energy and is therefore subject to the law of conservation of energy. And we're going to use this in equation form as our change in internal energy is equal to the heat transferred, subtract the work done. Heat transferred in, subtract the work done by the system. Okay, so remember your change in internal energy is UF, subtract U initial. That's going to help you with signs. This is work done by the system, and this is heat in. And I've included a little table there for you to help you with signs, because that's going to be important. In general, you can think of your system as having a boundary like a circle, and work going in is positive, and work done on a system are arrows into the circle. Anything coming out are work out is work done by the system, and heat out is work out. So then your U is going to decrease. If your system is doing work, your internal energy is going to decrease. If there's work done on your system, it's going to increase. If there's heat going in, your internal energy is going to increase. If there's heat coming out, your internal energy is going to decrease. So according to the first law of thermodynamics, a system's internal energy can be changed by transferring energy either as work, heat, or a combination of the two. So the thermodynamic processes discussed in the last section can therefore be expressed using the equation for the first law of thermodynamics as shown below. So our three processes are listed there. We have isometric process. In this case, we know that the work is 0, so your internal energy is going to equal your energy transferred as heat. Now, in say isothermal. In an isothermal process, your Q is equal to 0. So the increase in internal energy, your delta U, is going to equal your work. It's going to equal the negative of the work done by the system. Now, in an adiabatic process, the increase in internal adiabatic, your Q is equal to 0. Oh, shoot. I'm sorry. This is adiabatic. Remember, your Q equals 0. So your adiabatic, so in an adiabatic process, you have, now in isothermal, you have your internal energy isn't changing. So in an isothermal process, delta U equals 0, which equals Q minus W. So in an isothermal process, your heat is equal to your work. which we can remember because it happens really slowly so that it has time for that internal energy to not change. The last one is an isolated system. So your no energy is transferred as heat and no work is done by the system. So there's no change in the internal energy. So your initial internal energy must equal your final internal energy. Okay, so when you're looking at number one, you want to make sure that you see there's a few key words: large amount of ice water, and slowly. So that's going to give you a clue as to what process it is. And then you're going to use the first law of thermodynamics to determine Q. So in number two, we have the internal energy of a gas in a gasoline engine cycle decreases by 195 joules. If 52 joules of the work is done by the gas, how much energy is transferred as heat? Is this energy added to or removed from the gas? Okay, so our increase or our decrease in internal energy is negative 195 joules, and this is work done by the gas, so it has a positive value of 52 joules. When we put everything in, we know our internal energy is equal to our work, our heat, subtract our work done, and we end up with Q is equal to negative 143 joules. Now it's negative, which means this is energy that is removed. So this energy is removed from our gas. So go ahead and do the next few. They're extremely simple. The next thing we're going to talk about is a cyclic process. So a cyclic process is a thermodynamic process in which a system returns to the same conditions under which it started. So your net change in internal energy is 0. So your net heat transfer equals the net amount of work that you do. So two examples of these are a fridge, a refrigerator, and a heat engine. A refrigerator does work to create a temperature difference to transfer heat. A heat engine uses a difference in heat temperature, uses this transfer of heat to do work. So heat engines transfer energy from a high temperature substance to a low temperature substance. This transfer of energy, this change in Q, gives it, helps the engine to do work. This is an example of, say, the internal combustion engine in your car. Okay, so the net work that you do is can be equal to your hot temperature, subtract your cold temperature. This is also how the geothermal power plant out in whatever valley that is by Austin, this is how it creates energy. This is how it creates power. It uses the geothermal water coming in that's hot, and then it uses that energy to do work, and then it puts the water that is now at a cooler temperature back into the ground where it can get heated again. So no heat engine ever operates perfectly. You know this from your car. Only part of this available difference can do work. Most of the energy is still removed as heat. This is why engines get hot. They need coolants because of this problem. Okay, so you're going to look at some systems and identify where energy is transferred in heat and work and where changes in internal energy occur. And then you're going to answer if energy is conserved in each case. So when you look at the steam in a steam engine consisting of a boiler, a firebox, a cylinder, a piston, and a flywheel, for the boiler and firebox, Q is transferred into the boiler and firebox from the boiler into the cylinder and piston. This increases your internal energy. The piston and the cylinder then do work on the flywheel and your internal energy decreases. We know that energy is conserved all the time because you have to take into account when all forms of energy are taken into account. So then answer B, and we'll go on to the example. Okay, on number 8, a compressor for a jackhammer expands the air in the hammer cylinder to a constant pressure of 8.6 times 10 to the 5th pascals. The increase in the cylinder's volume is 4.0 times 10 to the negative 4th meter cubed. During the process, 9.5 joules of energy is transferred out of the cylinder as heat. So we have a pressure, our change in volume, and our heat transfer, which is negative 9.5 joules. It's asking us to first find the work done. So our work is going to equal our pressure times volume from last chapter. So if you take 8.6 times 10 to the 5th times 4.05 times 10 to the negative 4th, you end up with 350 joules of work. It's a positive that says that it expands. So when the gas expands, our work is done by the system. So this is a positive. So this is a positive value. Now we look for our change in internal energy. We have U is equal to Q, subtract W. So our change in internal energy is negative 9.5 joules, subtract 350 joules. This gives us a change in energy of negative 360 joules. Now, what process can this approximate? Well, if we look at our value for Q and our value for work, Q is extremely small compared to work. So this could we could look at this as an adiabatic process. Okay, that's it for section 10.2. We're going to talk about the second and third laws of thermodynamics next.